Knuth-Morris-Pratt, or in short KMP algorithm, is used to find a word in a text string. It takes advantage of the fact that by the time we get a mismatch, we may already have enough information to start the next attempt from non-first element of our word. In this video, I'll show you how to construct the prefix table used in the algorithm. Run the KMP string matching algorithm to retrieve a position of the first occurrence of a word in a text string, and briefly discuss the big O. KMP algorithm excels with small alphabet like that of the animal genetic code. Let's look at finding a DNA pattern in a section of a genome.
Okay, so the first thing we need to do before we can run the KMP algorithm is create a prefix table, T. The table stores values, integer values of the longest proper prefix matching the longest proper suffix at that position in P. The first thing we want to do is assign T0 to be -1 and T1 to be 0. -1 will be used later on in the computation. 0 simply indicates that the longest matching proper prefix and proper suffix in a word of length 1 is always 0. Then what we want to do is compare the proper prefix and proper suffix of the word CG. C is the only proper prefix in this word, and G is the only proper suffix. C does not match G, therefore the longest proper suffix length in this word is 0. Proper prefix matching the proper suffix length is 0. We move I one place, and now we have string CGC. The proper prefix that we are interested in is C, and the proper suffix that we are interested in is C. They do match, therefore the longest proper prefix and proper suffix is matching is length 1. We move J and I by one place. J simply indicates that the longest proper prefix at this stage is already at least 1. We have a word CGCC. We compare G with C, and they do not match. But before assigning 0 to the longest proper prefix and proper suffix matching, we move J one place to the left and check again. C is matching C, therefore the longest prefix matching the longest suffix is actually 1. Lastly, we have word CGCCG. We compare G with G. They do match, and we know that the previous character in the suffix and the prefix also matches. Therefore, the longest matching prefix with the proper suffix is of length 2. We do not have to compute another value of T, because that value would never be used in KMP algorithm, and you'll see why in a second. This is an example of KMP algorithm being run on inputs P being the pattern and string S being a string in which we are trying to find the pattern P. We also have a pre-computed prefix table T. M is an integer variable which indicates the starting position of our current attempted match of P against S. I is simply a position of current position in P currently being matched against S, M plus I. Let's start. C and C, they match. Therefore, we increase I by 1 and check the next position in P. G and G match. C and C match. C and C match again. G and G match. We're almost there, but T and G do not match. What we have to do now is change the value of M, and the way we do it is we check what M plus I is, which is 5, then subtract T I from it. So it's 5 minus T of I is 2, 5 minus 2 is 3. Now we have to update the value of I to be equal to T of I, which is 2. Now, instead of starting the matching from beginning of the pattern P, we can start it from the third position because we already know that C and G are matching. So T and C do not match. Again, we have to update M to be equal to 5 because M plus I minus T of I being 0 is 5, and update I to be 0. T and C, they do not match. Now what we do again is check M plus I, 5, minus 1, which is 5 plus 1, which is 6. So we increase the position of M, value of M by 1 to be 6. C and C, C and C, they match. C and G do not match. Therefore, again, we have to update position M to be 7 minus T of I being 0. And I to be equal to T of I, which is 0. C and C match. G and G match. C and C match. C and C match again. G and G match. And finally, G and G match, and we return M, this position in string S in which the words, the pattern P matches.
Complexity of the prefix table building algorithm is big O of n, where n is the length of the word. In the algorithm's loop, we either increase I and j, or fall back, decreasing j up to the number of times it was incremented. Number of fallbacks is strictly bound by n, and the runtime is hence 2n, or big O(n). Similarly, the search algorithm part has time complexity big O of m, where m is the length of the text string. While loop of the pseudocode has 2 branches. In each branch, we either increase I by 1 upon successful match, or we roll back up to the number of times we have progressed upon failure. And increase m by I minus the T of I, which is the new value of I. It is now clear that the algorithm runs in 2m time, or big O of m. Combining the two O's from both algorithms, we get combined big O of m plus n.